Hi everybody, thank you for joining us at our second webinar regarding the Fillamentum Flexfill family. Due to coronavirus precautions, I'm here alone, and the second part will be with Martin, our 3D printing specialist. My name is Martina, I work in R&D team, and I will show you something about the flexible polymers. So polymers are basically divided into three main groups. They are called thermoplastics, elastomers and thermosets. They differ in processing, recyclability and final properties. Thermoplastics are usually melted, the new shape is created, and to fix it, it needs to be cooled down. They are processed by extrusion, injection molding and also our known FFF 3D printing technology. Elastomers are processed under vulcanization temperature, and to fix the new shape they need to be heated at vulcanization temperature. Thermosets are also processed at lower temperature, and then to fix the new shape they need to be cured by heating UV in presence of oxygen or by mixing of two substances. And they can be also processed by 3D printing, but in SLA. With the processing, the recyclability is very much connected, because thermoplastics can be melted and cooled down again and again, but elastomers and thermosets have different behavior, because they connect and cross-link the net that is not reversible. Therefore, there can't be recycled. Final properties of thermoplastics are that they are usually tough, and to achieve the flexibility we need to modify them by adding of softwares, for example in case of soft PVC. Elastomers are elastic, flexible, we all know the rubbers. And thermosets, also known as resins, they are very hard and stiff, but also fragile. Thermal properties are connected with the structure. Basic thermoplastics are softening above certain temperature, for example PLA 50 degrees, ABS 100 degrees, etc. But elastomers and thermosets have created net that starts degrading above higher temperature. So how is it possible that we can print flexible materials? It's by the connection of thermoplastics and elastomers, and its new group called thermoplastic elastomers. The thermoplastic part gives us the melting and cooling down, the processing technologies, recyclability and softening above certain temperature, but the mechanical properties are given by the elastomer part. So, we will have a look on the chemical structure in more detail. On the picture you can see the yellow hard segment of the thermoplastic elastomer, and black is the soft segment. You can see that the hard segments are creating the microfaces and these little domains between the soft segments. Therefore, they don't influence so much the mechanical properties, but they are really important into the processing. When we add the temperature, we start melting the structure, the physical bonds are loosened, and the polymer chains are mixed with the soft segments. So the structure is more homogeneous under the temperature of melting. When we cool it down, the domains and microfaces of the hard segments are recreated, so we get back on the left picture. The soft and hard segments are different, like this or this. So I will show you the chemical structure of our flexible materials. Here is the structure of TPU. As the soft segment there is polyester and hard segment is polyurethane. Every type of soft and hard segment tell us the information how it will behave. Soft segment how it will behave in a mechanical way, and hard segment usually the chemical resistance. Here is TPE. It is formed from polypropylene hard segments and SEBS soft segment. And PBA is our last flexible polymer that is quite new. It is based on polyamide 12 hard segment and polyether soft segment. So we can see that it really differs a lot. Polyether, polyester, SEBS, they are totally different. Therefore, these flexible materials behave different in mechanical stress. And hard segments, polyurethane, polypropylene and polyamide leads to different chemical resistance. Now I will talk about the hardness. It is quite important to mention it as the first time because there is the list of our flexible polymers. We can see that Flexfill is like the flexible filament. Then we named it according to the chemical structure TPE, TPU and PBA, and the third part of the name is the hardness. It's 90, 92, 96, 98 short A. So it is really important to understand that hardness doesn't tell me anything about the bulk mechanical properties. It just tells me how hard is the surface. It's the property of the surface. So when you say that you need a harder material, it's usually that you need tougher or more stiff material. I have put there the picture how it is measured. It is on this little object with the rod with specific geometry. Shore A and shore D, which is the most usually measured, is with different geometries and different load. Therefore, it is very different. So as you can see on the picture, there is scale of hardness in shore A and hardness shore D. 80 shore A is approximately 30 shore D, 100 shore A is approximately 60 shore D. And our Flexfills are here in the picture. And there is clearly can be seen that, for example, Flexfill TPE is so specific by its mechanical property that 90 shore A means 30 shore D, because it has SEBS in its structure. So when we applied approximately 5 times more load and different geometry, it just doesn't resist so much that it should be about 45, but it's 30. And also TPE in high hardness, it has the second lowest value of the hardness. Then we can see, for example, that TPU 98A has 60 shore D, which is higher value than it should be, about approximate comparison. So we need to compare the materials in the correct way, the same measurement of the specimens, the same shore hardness. But this This property is often used in the nomenclature, also by the producers of thermoplastic elastomers, and therefore we also have the short hardness in the name of our materials. It's just for the connections, and right now I will compare 90, 92 and 90 short A to different chemical structure. So other property that is very specific for flexible materials is flexural resistance. I have these filables in here to compare the bending and flex. So we can see that P bar can be bended very well, TPU even more, that can be squeezed, and it has a very high reversible deformation, so we can squeeze it without any loss of the properties. But TPE is a little bit more resistant to this load that I apply. Is connected with these samples that I have, that P bar and TPU differ very much. P bar is very resistant to this load, but TPU can be squeezed very well. But in this object we can see that TPE can be also deformed quite well. So it always depends on the object that we have. We have also prepared specifically for the flexible materials these swatches that are for the comparison of the infill. We can see that P bar, TPE and TPU differ a lot. It is connected with the behavior that we have seen on filables. TPE is very well in high deformation with reversible shape. This is 30% of infill. It is really bendable well, and in 100% we can achieve tough materials, especially in case of P bar. TPE is a little bit more flexible and TPU is the most flexible. So it also is connected with the structure, and we can see that the hardness, as I said before, doesn't influence at all this bulk behavior. What is connected with the flexibility and bending is in the case of TPE, because of the polypropylene hard segment, is stress whitening. When we have a look on the object, we can squeeze it a little bit, but when we apply too high load, it starts to white. It's called stress whitening, and it is connected with the structure. It can be a little bit reversed, and it doesn't have influence on the properties or on something other. We also connect this chemical structure with the creating of neck. It is also in case of TPE that we apply the stress, and there is the thinner part of the filament. It's not in the case of TPU, it has very high reversible deformation. So this is how they differ. It's better to avoid higher elongation of TPE material. It is better to use TPU. There are also differences between the materials in cut and tear resistance. Tear resistance is a very high in case of TPU and P bar. You can cut it very hard by the scissors or knife, and TPE is a little bit less flexible, resistant. As I said that PBA has very high energy return. It is connected with the rebound resilience. On the graph there is the comparison of all 5 flex fills, and rebound resilience is the ratio of energy that is absorbed or returned by the material. It's measured on this kind of specimens, and when the pendulum is loads the specimen, the percentage of the energy that is returned is shown on the graph. So for example, PBA has 40% of energy that is returned and 60% of energy is absorbed. And on the comparison, TPE has about 15% of energy returned, so therefore TPE and also TPU is better for damping applications, and PBA is perfect for application when you need vibration transfer. So if we compare the chemical resistance of these 3 types of flex fill, we will see huge differences, because every polymer has its own good and bad solvent. We say that certain polymer is resistant against some substance and is not resistant against different substance. We try to don't say that something is the most chemically resistant, the best chemical resistance, and like this. We have prepared few substances to achieve the swelling or a little bit of dissolving of the object, and we have put it into these substances for 4 days, and we can have a look on it and compare it. According to the theory, we have found that the resistance should be, for example, good or bad in case of formic acid and isopropyl alcohol, but our test has shown something different, because it is also dependent on the 3D printing technology. Due to the layers that are connected layer by layer, it can have a higher influence on the printed object than it is in bulk, for example, made by injection molding. Then we can have a look, for example, in case of TPU and isopropyl alcohol, that the TPU is theoretically resistant to IPA, but in case of 3D printed object we can see little swelling, and it changes its dimensions. In case of formic acid, TPE has good resistance, TPU has swelled already after 1 hour, and PBA has a very hard swell after 4 days. In case of isopropyl alcohol, we can see that TPU has swelled a little bit and lost its became more transparent, and PBA has swelled to nice swelling. Acetone, theoretically TPE should swell, but it didn't come in this test. TPU has higher transparency, and P bar is the same. In case of ammonia, I won't open it because we don't have enough ventilation in this room, but there was good resistance in case of free flex fills, although TPU shoots well. And the last one is sodium hypochlorite, also known as bleach. And in case of TPE, there is a little bit of swelling. TPU should have good resistance, but it got yellow, and we can see that it got into the structure in the fill. And P bar just became more transparent. When we have a look on the temperature resistance, it doesn't depend only on the type of the material, which is TPE, TPU or P bar, but it also very much depends on the hardness. It can be seen on the picture. For example, comparison of TPE in two hardnesses, we can see that the range of temperatures where it resists is from -20, -10 degrees up to 120 or 125 degrees. And it's related with the hardness of the material. The softer material, the lower temperatures it can resist in both ends of the range. Regarding the low temperature resistance, the best is P bar. It's usually used for ski boots and some outdoor applications because it can resist up to -40 down to -60 degrees. So this is one of the best material for this application. Other property that we have a look on is density. As you can see the comparison on the graph, there is clearly seen that P bar has the lowest density. It's from all thermoplastic elastomers. TP is about 115 and TPU about 1.2, 1.23 kilograms per meter cubic. So P bar is the best for very lightweight applications where each gram counts. It is also a reason why it is widely used for running shoes and other sport equipment. And now we have a look on the rest of the properties. I will start with weather resistance because it is quite often question on our help desk. When we compare TPE, TPU and P bar, the best weather resistance in case of TPE, but also TPU. These two products that we have are different because TPU 98A is stabilized with a modifier that helps to increase the UV resistance, and TPU 92 and P bar has the lowest because they're not stabilized. But always to be sure that you can increase the UV resistance, pick the black color because the carbon black that is contained in the pigment, it helps to absorb the UV radiation and it increases the resistance. And it's also important that, for example, TPU, when it degrades on the UV, it doesn't lose its mechanical properties, it just starts yellowing, so therefore it doesn't have to be some issue for the application. Regarding the moisture sensitivity, you can see that PBA, because it's based on polyamide, it has very high moisture sensitivity. I have already mentioned it in our first webinar in tricky nylons, that nylons are very sensitive, and when you don't dry the filament, it starts degrading under the melting temperatures, and you will have different mechanical properties, different chemical resistance, and you won't achieve the properties you need. Also, TPU is very moisture sensitive, but TPE doesn't have any problem with absorbed moisture. For the food contact applications, you can use TPE or PBA. TPU is not recommended for these kind of applications. Also, I need to say that if you want to use our filaments for food contact applications, it needs to be tested on the final object. It needs to be tested according to the application and according in the conditions that it will be used. Other is gas permeability. The lowest gas permeability is in case of TPE. It's, for example, used as the sealings for the bottles. Transparency, you can also see it in these applications that TPE is not transparent or translucent. TPU and PBA are very transparent. If you want to have made printed object, you can have the TPE. It has very nice structure. All the free flex fills are very easily printable, and there is no viewable layer on the surface, so it's perfect. Also, regarding the low fumes release, it's better in case of TPE and PBA, but TPU may release a little bit of fumes, especially when the nozzle temperature is higher than it is recommended. But pay attention, because the fumes can't be smelled, but it doesn't mean that they're not harmful. And the last one that I will mention is low warping. TPU has the lowest warping, TPE has little higher, and PBA is the most tricky from these three materials, but it will be mentioned by Martin. So that's all from me. Thank you very much for watching, and the other part will be taken by Martin now. Thank you and bye.
Okay, hello, my name is Martin, and I hope you have enjoyed the first part with Martina, that you have learned lots of things about the polymers and flexible materials. Now the second part is up to me, so I have prepared for you some general tips for printing with flexible materials, also the basic settings for our flexible materials like TPU, TPE and the new released PBA. We take a look also on troubleshooting, and at the end I will show you some case studies about the usage of the materials and so on. So let's take a look for the general tips for printing with flex fills. For me, they are three mainly. It's a speed, it's a retraction, and it's a tension on the idler. The speed is crucial when you're printing with flexibles. Generally 20 to 30 millimeters per second is optimum value. Also, of course, it depends on the extruder you have. If you have an extruder which is made or designed for printing flexibles, you can run faster. The second one is tension. It's really important to release the pressure on the idler, because if you are pressing the flexible filament too much, it can be damaged, deformed, and they will be bigger, so it can run out of the extruder, and it results in failed prints. And the third one is retraction. For softer materials, I recommend to turn off the retractions. If you have the harder ones like 98 TPU from our portfolio, we are printing with retraction on, so it always depends on your extruder. And what is really necessary to mention, if you have a printer with Bowden setup, it should be quite tricky to print with flexible materials with unmodified extruder because of the play in the tube. So the 98 Shore A is definitely printable on Bowden settings with no modifications from our experience. And if you have the softer ones, maybe you have to switch from the direct drive extruder, which is better for printing, or you have to modify the extruder to be able to print it. Okay, so now I will show you some basic settings for TPU and TPE and their differences. So first of all, TPU. The printing temperature is around 220 and 240 degrees, 50-60 degrees on a hotbed. The print speed, as I said, it's 20 to 30 millimeters. It's a good start point. It always depends on your extruder if you are able to run it faster or not. This material should be cooled down quickly, so part cooling fan 70 to 100% is good. Hotbed surface, PI, mirror, glass, Kapton tape, it almost sticks to anything. As an adhesive, we used PVA glue stick or Magic Glue 3D lac. It's because usually TPU sticks too well to build surfaces, so these kind of adhesives are used like a separator for better removing the print from the hotbed. There is no need to use brim or raft for that material. Skirt is absolutely fine. No, also the heated chamber or enclosure is not needed because this material is easily printed on open space printer. Okay, I have also prepared a few basic tricks for printing with TPU. The first of all is adhesion. Definitely recommend to use PVA glue, Magic Glue 3D lac, Dymafix or something like that on your build plate, because usually TPU sticks too well on the build surfaces. So it works like a separator, so you can easily remove the printed part without damaging it. So it's highly recommended. Printing speed, regarding the show hardness, speed is usually the key of the successful print with TPU. So the more flexible material you are printing, the slower speed I recommend. Another important thing about the TPU is the hygroscopy of the material. So you need to store the material in the right condition, because if you leave the material in open space room, the filaments become wet and you will see the huge effect on the printed part. You will oozing, stringing, jamming the layers will separate very easily, and so on. So please store the material in proper condition in airtight bag with desiccants, and it really helps you with the perfect prints. Well, sometimes it happens that you have a wet filament, so depending on the hardness of the filament from our portfolio, if you have 98 Shore A or 92, the drying temperatures are 100 degrees Celsius for 3 hours for the Flexfill TPU 98 Shore A, and 80 degrees Celsius for 3-4 hours again for the softer variant 92 Shore hardness. So now let's take a look on the TPE and what is the difference in print settings against the TPU. If you look on the presentation, you can clearly see that the main parameters are almost the same or the same. The main difference is definitely the adhesion. So therefore we recommend to use large brim, and as that our TPE is based on polypropylene, for the adhesive we recommend Magigu for polypropylene plates or packing tape made of polypropylene, which ensure the good adhesion for achieving a good print. Okay. And I have prepared for you also some examples of possible use of Flexfill, what usually makers and we are printing from these materials. For TPU, it's definitely gaskets which are in contact with oils, carb fluids, greases, or something similar. It's protective casings for electronics or electronic devices. Lots of people printing RC tires. On the other hand, the TP is also for gaskets, but for the gaskets which are in contact with water, alcohols, hydroxides, lots of people print grippers or parts with direct contact with skin. Mobile cases, prostheses. And now is the time for new member of our Flexfill family. It's Flexfill PIBA. PIBA stands for polyether block amide. You can see the print settings for this material. So the printing temperature is 225 degrees Celsius to 245 degrees Celsius. What is different from the basic TPU or TP Flexfills is the heat bed temperature. It's 70 to 90 degrees Celsius because of the polyamide in this material. And what is also differ from the basic settings is the speed, because this material can be printed with higher speeds than the basic Flexfills. 20 to 40 millimeters, also up to 50-60 millimeters per second. Part cooling fan 0 to 50% to avoid shrinkage of the material. Heated bed surface, definitely recommend mirror or glass instead of PEI. Better adhesion you have, and it's better for your printing. For the adhesive, we would recommend PVA glue stick or Magigo for polyamides, and definitely quite big brim around the object if you are printing larger parts is necessary. So the difference between TPU and TP is definitely in speeds. In temperature on the hotbed, the adhesion is totally different, and the printability is better of this material. Again, what is necessary to mention that this material is quite hygroscopic, so storing it in proper condition is recommended, because if you want to achieve a great print results, the material must be dry. If you have a wet filament, you will see stringing, oozing, improper layer bondage, and so on. If you have wet filament, you can redry it for 3 hours at 80 degrees Celsius, and it should be okay. But after redrying, it's good if you leave the filament cool down in a stable environment with stable humidity, because if you put the material hot on the printer and print, the material absorbs again the moisture very quickly. Okay, and what is made from PIBA? For example, ski shoes, because they remain flexible below zero. Running shoes components due to energy return, cycling components, racket bumpers, shuttlecocks. There's lots of possibilities in applications with PIBA. Okay, and now it's time for the last part of our webinar. We will show you a few case studies of use of our materials like TPU, TPE and PBA from our partners from industry, hobby and design sector. The first case study is from Continental Automotive. It's divided into two parts. The first part is about the rubber insert on the robotic jaws, which are made from flex-filled TPU 92 Shore A. The original inserts was made from EPDM, and they broke after 3 weeks in mass production. So the main task was to extend the lifespan of this part. So the solution was 3D printed insert from our material TPU 92A. And the advantage of this material is that this material extends the lifetime of the inserts from 7 days to 200, so almost 7 months in production without any issues. So this is a huge cost saving and the cut in the lead time of spare parts. Also, the TPU material increased the reliability of the grip during the dynamic movements of the robotic arms, and also lowering the price. The price is about €3 per piece, so this is also a huge save. And now it's time for a second case from this company, which is about the squeegee of excess oil during the production of electric vacuum pumps. The material used in this case study is the Flexfill TPU 92 Shore A, and the aim of this case study is to produce a squeegee for excess oil in the manufacture of shafts for vacuum pumps. The main requirements for the application was resistant to oils and wear resistance, because the shafts for vacuum pumps is dipped into the bin with oil, and the squeegee removes excess oil from the shaft. And there are also the small fins on the shaft which can damage the squeegee, so the wear resistance is also important. So that's from Continental company. Now I will show you a small case study for Flexfill TPE. It's from hobby sector. It's about a coffee cup sleeve, which are made for cups for hot coffees or hot drinks. And the main requirements for these applications are the certification for food and skin contact, so there is no issue touching it regularly. Also the high temperature resistance, so there is no worries about pouring hot drinks like coffee, tea or whatever you like. And what is really great about this material is that's very pleasant to touch. So we have made some cups with sleeves and also the grips. And what is also great, that you can make customized grips for different occasions, and without worrying about the skin contact application and temperature or whatever. So let's take a look on the last case study we have prepared in this webinar. It's about the use of Flexfill PBA and 3D printed sole for training shoes. The main aim was functional prototype of sole for training shoes in hands with sensor. It was made in cooperation with Mr. Oldřich Vojta from University of Zlín, focused on shoemaking. And the PIBA meets all the requirements the designers and makers have for this sole. So it was flexibility, energy return, to be strong enough under the load, and there is built-in sensors in the sole, so the PIBA protects them, and the sensors measuring the temperature and the humidity. So the athletes have the information about the humidity and the temperature to prevent injuries and also dermatological issues from the humidity. And on the picture you can see the complete design with use of PIBA. So I think this is really interesting. And well, this is all from today's presentation. So I hope you have enjoyed all the parts of our webinar. You have learned lots of things, and I would like to thank you for your attention. And if you have any questions or any issues with printing, just let us know at helpdesk@fillamentum.com. And see you next time.